Hello and welcome back to another Calculus 3 multivariable calculus video. Today we're going to be going over vector fields. This one's going to be a short one today. So I guess just diving right in, what is a vector field? A vector field, or you might see it abbreviated as, just to save time, VF it's a vector function. Oh, well, what does that exactly mean? Well, it's a vector function that assigns a vector to every point in a subset of some kind of space, right? So each point on a given plane may be modeled with a vector field. So given a vector field, we can plug in 0, 0, 0, 1, 1, 0, going on. We can plug any point into that vector field, and then it'll give us a vector at that specific point. So basically what it's going to be doing is, well, if we give it some point in, let's say 2D, well, it's gonna, that point, that xy point, it's gonna have a vector attached to it, and that vector is gonna represent direction and the magnitude of that vector. We'll talk a little bit more about how we're gonna figure out what the magnitude is, but we've taken calculus 2. We know what the equation of the magnitude of a vector is, so it can kind of be intuitive to understand that, well, depending on the vector field, and certainly on the ones we're going to be looking at today, the further you get from the origin, it's probably going to get more magnitude. So the arrows or the vectors are going to get larger. So I guess that's how you can explain what a vector field is. So I guess why, there's a couple of applications here, namely gravity fields. Gravitational fields, there's going to be a vector pointing toward the center of whatever gravity field you're in, right? So on Earth, well, there's going to be a vector pointing toward the center of the Earth with that magnitude being whatever 9.81 meters per second squared. That's going to be a gravitational field. So I guess that's kind of a gravity, but realistically, there's a bunch of different applications of it. Fluid dynamics kind of like how water flows through a pipe, or some kind of shape, how water flows through it, and kind of more in like a meteorologist sense. It tracks wind patterns, right? So it tracks the intensity of wind, and it also tracks where the wind is going, right? So it's kind of like that. And I'm sure if you've ever seen the news, and I'm sure we've all seen a vector field, we just didn't know what it was called yet formally, right? Electromagnetism is a big one. Whenever you're taking physics 2, well, the magnets, that's going to be a magnetic field, right? So if we have a positive and negative magnet, well, then they're going to be attracting each other, right? That's a magnetic field. So it's kind of electricity and magnetism. They exert forces on charges. So I guess overall, there's a bunch of different applications, really, of vector fields, but the main one that we can just think of, it's basically a force map. To put it simply, it's a force map, right? So I guess the next question is how? Well, we're going to have some kind of function, a vector-valued function, wherein our x correlates to another function, f of xy, and the y component of our vector correlates to a g of xy, right? So you can definitely model these in 3 dimensions. For the sake of simplicity, and honestly, we're not really going to be doing too many 3D vector fields within Calculus 3, at least not right now. So we're definitely going to be sticking with 2-dimensional vector fields, and we'll definitely understand why that is in just a little bit. But basically, it's pretty hard to draw a vector field, right? So it's a force map, but every single point on that force map has a length, it has a magnitude and a direction, meaning depending on it, on what function you're mapping there, well, your vector field may just look like a bunch of arrows overlapping each other. So we're going to pretty much find out that, well, vector fields are a little bit harder to graph than it may be seen. So I guess getting into our first example here, we have the vector field of xy. Pretty simple one here. How are we going to draw this? Well, to put it simply, the way we're going to draw this is just we're just going to plug in points into our vector value function. So what points are we going to plug in here? Well, I think I want to plug in, we'll do a little circle around the origin. So we'll do an origin, I guess more like a cube. So we'll plug in those. That should give us an okay idea of what's going on. We'll also plug in a little bit of some more extravagant ones here. Here. We'll go here. And we'll go like over here. Okay, well, starting off, we're going to have the point 0, 0. We're going to have 1, 1. We're going to have negative 1, 1. We have negative 1, negative 1. We have 1, negative 1. That's kind of our little circle there. Might as well, we'll throw in that 2, negative 1 right there. Then we'll throw in that 0, negative 3. Oops, I slightly extended over. That's okay. We're going to do that negative 3, 1. Finally, we have some scale here. Okay, well, pretty simple vector field here. Well, whatever we plug into our x and y, well, that's just going to be our vector field, right? So at the origin, it's going to be the vector 0, 0, 1, 1. Just plugging in these x and y points is pretty standard right now. Negative 1, 1, negative 1, negative 1, 1, negative 1, 2, negative 1, 0, negative 3, negative 3, 1. Okay, so those are our different vectors. Well, let's just start off down the list here. Well, what does this 0, 0 look like? Well, there is no vector. It has no length, it has no magnitude, and it has no length, no direction there. So we're done that one. Add 1, 1, so that's going to be this point right here. Well, our vector points in the direction of 1, 1. Okay, it's not going to be too large of a magnitude. We'll just keep it like that. Okay, that one's done. At negative 1, 1, well, that's going to be this point right here. Looks like it's the exact same thing, so negative 1, 1, so therefore it points in the negative direction, and up 1. Try to make it a little bit kind of standardized here. These all should hypothetically have the same magnitude, and we'll talk about that. Negative 1, negative 1. Looks like this is going to point in the negative 1 direction. Same magnitude as the other two, roughly. 1, negative 1, same thing. Okay, 2, negative 1. Let's go ahead and do this one. Looks like it's going to go to the right 2 and down 1. It's going to be a little bit larger here. It's not necessarily going to be like that. It's going to be more like this. Definitely a little bit of a larger arrow there. Interesting. 0, negative 3. Okay, well, that's just going to go down 3 all the way. It's going to have the square root of 3 be its magnitude. Or 3 be its magnitude. So it's going to be the largest arrow that we've had so far. And then negative 3, 1. It's going to point in the negative x direction and up 1. So this is going to be something like that. Okay. So this is kind of our simple vector field that we've kind of created right now. Well, it kind of looks like all the points are pointing away from the origin, and maybe we can just kind of like visualize what's going on here. Well, let's do one more extreme example here. We'll go to point 3, 3, which is going to correlate to 3, 3. Oops, I messed up my color coding there. Okay, well, that is going to be pretty large here, but looks like it's going to look something like that. Okay. Well, how do we know what the magnitude of these are? How do we know the length? Well, we know that the magnitude of whatever our function here, our vector field, is going to be the square root of the x value squared plus the square root of the y value squared. So what is this saying? Well, this is saying that the closer we are to the origin, the smaller the arrows are going to be. And the further away we are, well, that's how large they're going to be. So I guess I kind of tried to model that there. Perhaps I didn't succeed too well, but we're pretty much just going to have little arrows here, right? This is just kind of me filling in this other color. And then as we go on, well, the arrows are going to get larger, right? So we can kind of model what this may look like if it were like completely accurate. So it may look something like that. And like I said, we can kind of just notice patterns here wherein we're like, okay, well, what are the patterns here? Well, first of all, we can kind of see that it always is pointing away from the origin, no matter what. And there's going to be a name for that. Might as well just give it to you right now. This is an example of a radial vector field. Let's go ahead and write that down, a name here. It's going to be a radial vector field. That just means that whatever our vector function given here, it's always going to point away from the origin. And like I said prior, well, the magnitude, the length of these vectors is going to be increasingly great the further from the origin it is, right? So I guess another point that I just kind of want to make here is, like I said, we're not going to be making these like to scale, right? We cannot make these perfectly accurate because, I mean, let's just do an example in like red here. Well, what would it look like if I was like truly doing a vector field properly? Well, the arrows would be overlapping here, right? They would be increasingly large, but they would just be overlapping. So it would be kind of difficult. And that's just kind of like a model, but it's increasingly difficult to kind of model this vector field. And that's kind of what I was talking about, is we only have so much ability to model these things. So that's our first vector field. That's called a radial vector field, like I said. So let's go ahead and move on to the next example. Okay. Given the vector field f of xy is equal to negative yx, well, let's go ahead and use the same kind of strategy we used in the other one. We know what the origin is going to look like, but we'll put it down anyway. Let's make a little box around our origin here, and then we'll switch it up this time. We'll do 3, 0 and negative 3, 0. And then we'll do 2, 2. Maybe we'll do 2, negative 2. And let's do one funky point. We'll do 3, 3 up here. Okay. So those are our points here. Well, we have 0, 0. Oh, did I change my color coding? I did. We flipped it. That's okay. We're going to have 1, 1, negative 1, 1, negative 1, negative 1, and 1, negative 1. Oh, that center point done there. And then it looks like we had 3, 0 and negative 3, 0. We had 2, negative 2, 2 and 2, negative 2. And then our one funky point was 3, 3. Okay. Well, same kind of concept here. Well, let's go ahead and plug in our values. Well, we have the vector function negative yx, meaning these values right here are going to correlate to the x component. So I'll just kind of underline all those in purple, I guess. And then we'll do these ones in green. That's going to correlate to the y right here. Okay. Well, writing our vector fields, well, we're going to have 0, 0 here regardless. Looks like our first one is going to be 1, but it's going to be negative now, so it's going to be negative 1, 1. This one looks like it's going to be negative 1, negative 1. Negative, negative 1, that's going to be 1, negative 1. Negative, negative 1 again, that's going to be 1, negative 1. Looks like this is going to be 0, 3 right here. 0, negative 3 this time. Negative 2, negative 2. Negative, negative 2, that's going to be 2, 2. And here we're going to have negative 3, 3. That's what our vector field kind of looks like. Well, I'm going to just kind of highlight the components here. These are all going to be negative, made negative, I guess. So negative 1, just kind of like a proof check. Negative, negative 1, that's going to be 1. Negative 1, negative, negative 1, that's going to be 1. 0, that's going to be 0, 0. negative 2, that's going to be negative of negative 2. It's going to be negative 3. Then these are pretty self-explanatory. It's just going to be exactly what it was here. All right, looks like we have our vector field. A couple of vector points here. Well, let's go ahead and draw them. Different colors last time. Let's do it. Well, that 0, 0 point, well, that's just going to be 0, like we said earlier. Okay, 1, 1. That point corresponds to negative 1, 1 now. So it's going to be pointing in the negative direction, and it's going to be up 1. Okay. So that one's completed. Negative 1, 1 now. Well, it's going to be pointing to the negative x direction, and now in the negative y direction, meaning it's going to be looking like this. Negative 1, negative 1. It's going to be pointing in the positive y direction, in the negative, or no, sorry, positive x direction, in the negative y. 1, negative 1, that looks like it's going to be pointing in the positive y direction, or positive x, and the negative y. Did I do that one right? That's 1. Oh, that's 1, 1, sorry. I was about to say, like, that's kind of breaking the pattern here. You know what I'm saying? It kind of looks like it's going to be pointing in the clockwise or counterclockwise direction here. Okay. 3, 0. Looks like that's going to correspond to 0, 3. So, interestingly enough, wait, what? 3, 0. Yeah, there we go. 0, 3. Okay. Should be done. Negative 3, 0 is going to be pointing in the 0. Negative 3 direction. I'll try to make those roughly similar. Did I hit? Yeah, I actually kind of did a good job of that one. Alright, negative 2, 2. Looks like it's going to be pointing in the negative, negative direction. Okay. And then in the 2, negative 2, looks like that's going to point in the positive y, positive x direction here. And then 3, 3, our funky point, that's going to point in the negative x direction in the positive y. Okay. So, kind of looks like we can kind of model this. Well, these look exactly, it looks like it's just going to be rotating counterclockwise here. And I guess maybe we'll be able to notice some trends. Well, if it's in the first quadrant, as a matter of fact, if it's in the first quadrant or the fourth quadrant, well, it looks like our y is going to be pointing up because it's the positive x. So if x is greater than 0, then it looks like our vector is going to be pointing upward, and inversely like that. So I guess we can kind of make like a trend thing here, right? So, well, if our x is greater than 0, that's everything over here. Well, what's a trend here? Trend here is that they're all pointing up, right? Okay. Well, if our x is less than 0, what does that look like? Well, that's going to be everything over here. Everything over here is pointing down, okay. And kinda, well, we'll keep it green so that we can recognize these trends. Well, if our y is greater than 0, is there any trend here? Y greater than 0. Assuming y isn't 0, then it's going to be pointing to the left. If y is equal to 0, then stagnant, and then if y is less than 0, that's going to be everything down here. It looks like it's going to be pointing to the right. And I guess I should have done an x is equal to 0 case here. If x is equal to 0, then I actually didn't do any of those, huh? Well, let's do one real quick. We'll do 1, 0. That is going to correlate to, what's our vector field here? Well, that's going to correlate to 0, 1. So for x is equal to 0, it looks like there is no x slope here. Okay. So we kind of have what it's looking at here. Well, just kind of basing on off the trend, well, looks like we can just kind of like map the rest of this. Obviously it's not to scale quite. I should probably make it to scale. But regardless, following these trends, well, in the first quadrant, that means x is positive and y is positive, meaning if we combine these two, well, it's going to look roughly something like that. So everything in this field is going to look something like that. Okay, well, if our x is negative and our y is positive, then combining these two, then it looks like it's going to be down and to the left. That's something we can kind of observe here. Okay. If our y is negative and our x is negative, well, what does it look like from there? It looks like it's going to be down and to the right. And finally, if our x is positive, it's going to go up, and if our y is negative, then it's going to go to the right. Well, looks like it's just going to be spinning in a counterclockwise direction there. What this might be called is a rotational vector field. So I guess that's kind of a strategy that we can do when we're doing these. Well, we can kind of recognize the trends there by just drawing a few points. We can recognize some trends, and I kind of did that over here, but it was more intuitive since it was just x, y, right? Whatever our point is, what our slope is going to be. So I guess that one was kind of more intuitive, less so for this one since it could mess us up a little bit since, you know, it flips the variables and makes one negative. But overall, what does this one look like? Well, just kind of like an overarching thing. Well, if this is our origin, well, it looks like it's going to spin. It's going to get larger and larger, right? It's just going to kind of look like something like that. Thus, the rotational vector field. That is an introduction to vector fields. This is something that is very important in modeling and applications. We'll definitely talk more about these in a few videos. Thank you.